Always, sometimes, never. Let A and B both be n by n matrices and both be invertible. That means that A inverse and B inverse exists. C is A times B, and we want to decide whether C is always, sometimes, or never invertible. Well, I think it's always invertible. And to prove this, what I'm going to do is I'm going to try to determine what C inverse actually is in terms of A inverse and B inverse, and then show that it really is the inverse of C. So I'm going to let D be equal to C inverse. If it is, then C times D has to be the identity, and D times C has to be the identity. But let's try to figure out what D might be. Well, I'm going to claim that D is B inverse times A inverse. Now, if I take C times D, that would be A times B times B inverse times A inverse. But we're allowed to associate. So this is equal to A times B inverse times A inverse. But this is just A times the identity times A inverse. But this is just A times A inverse, since any matrix times the identity is the matrix back, which is the identity by definition of inverse. And so, yes, it is true that C times D is the identity. If I look at D times C, that would be B inverse times A inverse times A times B, which is B inverse times A inverse times A times B, which is B inverse times the identity times B, which is B inverse times B, which is the identity. So it is true that if I take C and I multiply it by D, or D and multiply it by C, then I end up with the identity. And so by definition of inverse, D is C inverse. So, done.